Get started. So welcome everybody to our weekly seminar. We're very happy to have Shai from Weizmann tell us about bootstrapping N=4 super mills on the conformal manifold.
And thank you, Leonardo, for the invitation. This is based on a paper that actually came out a couple weeks ago with Silvio and Ross. So it is no longer to be announced. It is now out. Great. So let's get started. So let's begin by defining what N=4 super mills is, although I assume most of the audience will be familiar with it. So N=4 super mills is the max-split supersymmetric gauge theory in 4 dimensions. And it's defined by the gauge group G, for instance, SUN, which is what we'll take for most of this talk, the Yang-Mills coupling G Yang-Mills, and the theta angle. And so what's nice about this theory is that it's conformal for any value of what's called the complexified coupling, which is where you combine G Yang-Mills and theta as such. So N=4 super Yang-Mills is one of the most well-studied toy models in high energy theory for many reasons. One reason is due to ADS-CFT. So it's dual to type 2B string theory and ADS5 crosses 5, where you have a gravity description when n is large and the tough coupling is large. And so it's kind of the paradigmatic example of ADS-CFT. Another more general motivation, though, is that it's just the simplest in the sense that it's the most symmetric gauge theory. And so if you're somebody who's just interested in studying gauge theory, such as QCD, but you want to have a much slightly easier time, then you can study N=4 super Yang-Mills, because you can compute the most things in it. But even though it is simpler, it is still not simple, and it is still very hard to study. It's still a strongly coupled conformal field theory. So there are various perturbative approaches. So we have these 2 parameters, n and tau, and you can try perturbing in either of them. So the more standard perturbative approach is just weak coupling. So if G Yang-Mills is small, then like any 4D gauge theory, you can compute things using Feynman diagrams, and you can get an expansion. Usually it's conventionally expanded in the tough coupling lambda. And you can do this for any value of n and for any gauge group. Another much more subtle, but nonetheless perturbative approach is integrability. So this is perturbative in n, but finite in lambda. And in particular, in this limit, it does not depend on theta. That's why it's only for the tough coupling. And so both of these methods are very powerful, but their limitations is that you cannot probe the quantum gravity regime, which is where n is very large, but nonetheless not infinite, of the string dual. So to say it another way, integrability studies the classical string, but it has more difficulty studying the quantum string, which are the 1/n corrections. And so we would like to have some method which can work at both finite n as well as finite coupling. And so prior to this talk, there are 2 known non-perturbative methods for finite n and finite coupling. The first one being Superspencer Glocalization, and the second one being the Numerical Conformal Bootstrap. And so I will briefly review each. So first, let's talk about Superspencer Glocalization. So this method uses the Lagrangian of the theory to compute protected non-local observables exactly for any value of n and tau. It's initiated by Pester. So for instance, people computed the half PPL-Wilson loops for any value of n and lambda in this famous paper by Drucker and Gross. For these specific quantities, there was actually no dependence on theta. So there was no Instanton contributions. A different quantity computed in the original paper by Pestun is the sphere free energy deformed by a mass, which actually breaks the supersymmetry to n=2 from n=4. But nonetheless, you can still compute it. So note that localization does not require conformality because you can do it even though you've deformed by mass. And this result is in some sense more non-trivial than the Wilson loop result in that it depends both on n and tau. In particular, it depends on theta. So it receives contributions from instantons, and these instanton contributions are summed up by something called the Nekrasov partition function, which we'll describe in more detail later. The limitation of localization, though, is that it cannot compute unprotected observables. Another limitation is that you can't compute, at least directly, local CFT data, such as scaling dimensions or OB coefficients, unless, of course, the scaling dimension is just trivially fixed to be an integer or something like that. And so the advantage of localization is that it depends on n and tau in a known way. The disadvantage is that as bootstrappers, as people who are really into local CFT data, we don't know how to directly relate it to local CFT data. So the other non-perturbative method is the numerical bootstrap. So as everyone here knows, this gives non-perturbative bounds on CFT data. So in particular, when applied to n equals 4, the simplest case is to look at the stress tensor 4-point function. And as Leonardo and collaborators showed, you could compute bounds in terms of the central charge C, because C is related to certain OP coefficients. You know how to put it into the bootstrap. For the case of SUN, C is just n squared minus 1 over 4. So this allows you to put in the value of n. And so here I show these two very nice plots from Leonardo's classic paper. So they were able to compute these bounds for any value of n. And so on the right-hand side, you see zooming into the large n regime. So this is 1 over C. And one of the successes of this study is that you could see that these upper bounds seem to be slowly converging to the leading 1 over C correction, or the leading 1 over n squared correction, which can be computed from supergravity, and which does not depend on tau. The limitation of this study, though, is that they didn't know how to input the value of tau into the bootstrap. And so their bounds were applying to the entire conformal manifold. And the reason why it was hard to put the value of tau into the bootstrap is that there is no local CFT data, which at the time was known exactly in terms of tau. Now, of course, all local CFT data depends on tau, but in some very complicated way. And so you don't know how to put it in some non-perturbative. Okay, so that's the review of the previous numerical bootstrap studies. So the new idea of this talk is just to combine these two non-perturbative approaches, which is localization and bootstrap. So in the last few years, with various collaborators, I derived two exact relations between the mass to form free energy, the thing which localization computes, and certain integrals of the stress tensor 4-point function. Now, previously, we had applied these integrated constraints to the stress tensor correlator in a large n expansion. And that allowed us to compute the first few coefficients in this large n expansion, being dual under ADS-CFT to scattering of gravitons, where the lowest term is the Einstein-Hilbert term, and then 1 over n corrections would then correspond to higher derivative corrections to Einstein gravity. So in particular, the first higher derivative correction comes from the Riemann tensor to the 4 term called R to the 4. The next one comes from acting with various covariant derivatives. So we were able to compute these corrections at finite tau by computing them in the CFT and then interpreting them in ADS. And when we took the flat space limit then of this ADS holographic correlator, we could compare it to the type 2B S matrix in 10 dimensions, whose first few corrections had been independently computed in the past, and we found a very nice match. And so this was the first non-perturbative in coupling check of ADS-CFT. But all these previous applications were they were all perturbative in the sense that they were perturbative in n. So we were using a non-perturbative tool, which is localization, and bootstrap, but using it in a perturbative sense. And so the obvious question was like, well, if we have non-perturbative tools, why don't we just use them non-perturbatively? And so that's what the goal of this talk is, to do everything non-perturbative. But for that purpose, we can no longer get nice analytic results. Now we are going to have to get numerical results using the numerical bootstrap. So I should note that this idea of combining localization with numerical bootstrap was done before, also by me and Silviu, this time with Nathan Ogmon. In the previous case, we had studied ABGM theory in 3D, which is also a nice, interesting theory. It also has a holographic interpretation. The reason why ABGM, though, was easier is that in that case, the localization quantity was a certain OPE coefficient. And so it was very easy to put into the bootstrap. The reason why n equals 4 was much harder is that, as you will see in the next few slides, now the localization quantity is not related to a specific OPE coefficient. It's related to, in a sense, an average over all OPE coefficients, because you're taking an integral of the full 4-point function. And that's why it requires kind of like new technical tricks in order to combine with the numerical bootstrap. And that's why this project took 3 years. Okay, so let me give an outline of what the remainder of the talk will be. First, we're going to review the stress tensor 4-point function and previous weak coupling results for the CFT data. Then we're going to discuss these two integrated constraints and how to compute the localization inputs in terms of matrix model integrals. Then we're going to show how to combine the integrated constraints with the usual crossing constraints of the numerical bootstrap. And this will include lessons for general space-time d greater than or equal to 2. Because I want to emphasize that this talk, while mostly focused on n equals 4, I think holds some general lessons that should be useful for many dimensions, many different theories. Finally, we're going to show bounds for the lowest dimension scalar, which at weak coupling is called the Konishi, for any value of n and tau in principle, although in practice, we focus on n equals 2 and 3. So the SU2 and SU3 theory, but we did do for any value of tau. And in the weak coupling regime, we're going to show that we can match these weak coupling results to 4 loops, which is a very non-trivial check that we're really bootstrapping the physical theory. Okay, so any questions about the introduction and the outline before I jump in? Okay, great. So hopefully everybody is following so far. Okay, so let's start with some basics about n equals 4. So all n equals 4 CFTs have an SU4R symmetry and are conformal manifolds with one complex parameter tau. The reason why this is true for any CFT, even abstractly, is because the complex marginal operator appears in the stress tensor multiplet. So you're forced to have it. You can define n equals 4 CFTs by the values of their central charge, which is the dimension of their group divided by 4, as well as this complex tau. So we are interested in a specific n equals 4 CFT called n equals 4 Superior-Mills. This is a gauge theory where matter transforms in the adjoint of the gauge group G, which must be a compact classical Lie group. And for this talk, we're going to focus on the case G equals SUN, although the method we're discussing could be used for really any group. SUN is just because it's the most famous one. Another fact about n equals 4 is that this conformal manifold has a duality group, which for the case of SUN is simply SL2C. And so under this duality group, there are two self-dual points. One of them is when tau equals I, in which case you have an enhanced global symmetry of Z2. The other case is when tau equals e to the I pi over 3, in which case the enhanced symmetry is Z3. So the specific quantity we care about in this theory is the stress tensor correlate. So as usual in the superconformal bootstrap, it's convenient to study the superprimary of the stress tensor multiplet, which is a scalar. So we call it S. It transforms under the R symmetry in the 20 prime representation. And so we write the 4-point function, factoring out the x's, as the usual function of conformal cross ratios, U and B. We then impose the constraints of superconformal symmetry by solving the superconformal ward identity. So as shown by Dolan and Osborne, there's a very nice formal solution, which is that you can write this 4-point function in terms of some short piece, which does not depend on tau. So that means in particular, you can just compute it from the free theory by looking when G-Mills is 0. So it's kind of trivial. Then there's this theta term, which is completely fixed by symmetry. And then all the interesting dynamical stuff is this function T of U and V, which notice does not depend on the R symmetry indices anymore. And so that's kind of nice and simple about n equals 4. So as usual in the bootstrap, we expand the 4-point function in blocks, where in particular, we're going to expand this function T of U and V, because that's where all the interesting information is. So when we expand it in blocks, there are two kinds of multiplets that appear. There are short multiplets, which do not depend on tau. Thus, you can just compute them from the free theory once and for all, and then resum their OP coefficients to get these exact functions F0 and F1 short. Where notice that their dependence on C is also very simple. They're just linear in 1 over C. So these things were actually computed in the original paper by Rosselli et al. The more interesting stuff is the long multiplets. That's this first term. And so as you see, up to this factor of U to the minus 2, this is just and the shift by 4, this is just a usual 4D block expansion. And so for every even spin L, we have a different long multiplet, in fact, a tower of long multiplets for every possible twist. And so the goal of any non-perturbative study of n equals 4 is to compute these scaling dimensions and OP coefficients. That is the non-trivial information in the 4-point function. So let's first review some perturbative results about this 4-point function. So in the free theory, when lambda is 0, you have long multiplets of every twist, even twist, 2, 4, 6, etc. And the stress tensor 4-point function has been computed to 4 loops in a small lambda expansion for finite n. Where these are the authors who did the 4-loop thing, including non-planar corrections. Of course, there's many, many other authors who did previous loops and other related stuff. So one kind of interesting fact is that the first non-planar correction, i.e. the first 1 over n squared correction when expressed in terms of lambda, actually only appears at 4 loops. So prior to 4 loops, if you only knew about the planar theory, you were actually good. So like the 4-loop term is really kind of non-trivial. So if you know this 4-point function, that means in principle you can expand any CFT data from it. So in particular, you could expand the scaling dimension of the lowest dimension scalar operator, which is called the Konishi. This was done by Velajanin, and this is the answer for its scaling dimension. So as you see, these first 3 loops, n does not appear because it's completely planar, and you only have a 1 over n squared correction at 4 loops. You can similarly extract CFT data for all the lowest twist operators of any spin, although we're not going to use that in this talk, although we will be using the OP coefficient of the Konishi. As I mentioned in the first slide, there's another method, perturbative in n, called integrability, and this allows you to compute the scaling dimensions of any single trace operators, such as the Konishi, for any value of lambda. In particular, there's a very nice method called the quantum spectral curve developed by these authors, which allows you to very efficiently compute it, also for higher spin operators, etc. Although we will not be making contact with that result because we're mostly going to be talking about finite n in this talk. Okay, so as usual in the Bootstrap, you want to know how many relevant operators there are. So let's discuss the number of relevant operators when n equals 4 supering those. So we already spoke about one relevant operator, which is the Konishi, which at weak coupling has dimension 2. So it's below 4. So to try to see what the next relevant operators are, let's look at weak coupling. And so the next lowest operators are dimension 4 and spin 0. And at weak coupling, there are 4 of them. And so their degeneracy was computed and unmixed by these authors at one loop. And the one loop correction is given by the solution of this quartic equation, because there's 4 such degenerate operators. I should note that there's 4 such degenerate operators when n is bigger than 2. When n is specifically 2, there's actually only 2 degenerate operators. And that's why there's only 2 solutions for n equals 2. So an interesting fact about these solutions is that only one of them is negative for any value of n. And so this means that at weak coupling, there's only one relevant operator coming from these dimension 4 guys, because all the other ones are 4 plus something. So that means in total, at weak coupling, there are 2 relevant operators, the Konishi, and then one linear combination of these dimension 4 guys. Another limit you can look at, so this is weak coupling. You could also look at the limit at large n and finite tau. In that case, you can use general intuition about large n to see that 3 of these operators drop from the spectrum because they involve single trace operators. Similarly, the Konishi drops from the spectrum because it's single trace. And so the only guy that survives is a double trace operator, which is the one that's relevant. So that means in the one limit, which is large n and finite tau, you see there's one relevant operator. And in the other limit, which is weak coupling, you see there's 2 relevant operators. And so it's reasonable to conjecture that probably for any value of n and tau, there's at most 2 relevant operators. Although this is a guess. We don't know for sure. Okay, so that concludes the review of the weak coupling results, which we're going to use. So any questions about those before I move on?
Maybe you say large n and finite tau, but
yeah.
Should it be large n and finite lambda? Like the planar theory in principle is only like planarity, planar arguments. I thought they would only arise at finite lambda and large n.
Well, the large n arguments you can actually use in either the strong coupling tough limit or the finite tau limit. Like the large n arguments work in either case. In fact, at large n and finite lambda, it would be, like that would in some sense be a more non-trivial limit, because in that case you actually do have single trace operators contributing. So but also in that limit, you can also check, at least from integrability, there's only 2 relevant operators.
But should you not say that at large n and these operators, they get a large anomalous dimension?
Yeah, that's what I'm saying. So I'm saying at large n and finite tau, all like 3 of the 4 operators just go off to infinity, and so they're very obviously not relevant. And there's only one operator which has a finite dimension, which is the double trace guy, and in particular, it's relevant.
But how do you know this happens at large n and finite tau?
Because you can do the calculation at large n and finite tau.
But then you're using some planarity, right? Some planar diagrams to dominate.
Yeah, but you can also go beyond the planar limit. You can do to any order of monogram. Yeah, I'm just saying that
Alt is complaining that if a large n infinite tau, you cannot use integrability. So how do you do the calculation?
But we're not using integrability for large n infinite tau. In fact, you can't use integrability for that limit.
That's the point. Yes.
Yeah. Integrability is a different limit. So integrability is the tough limit. I'm talking about a different limit. This is called the very strong coupling limit. It's somewhat less familiar. This is the limit where it's large n, but Yang-Mills is kept finite.
Okay. And so how do you see these large anomalous dimensions? How do you do the computation? Because there must be some diagrams that drop out.
The calculation, at least in the supergravity limit, is completely identical to the strong coupling tough limit, because the 2 limits are exactly the same at leading order at large n.
I see. So you compute them holographically, you say?
Yeah, holographically, yeah, for instance. Yeah, you could think of this large n finite tau limit as like dual to strongly coupled type 2b string theory, but nonetheless in the Einstein gravity approximation.
You're saying that because lambda is large, I'm justified in using classical supergravity.
Well, yeah, because n is large.
Yeah, well, because from the ADS-50 dictionary, the curvature of the 10 background is small.
Sure, sure. Yeah,
yeah.
yeah, yeah. You could also say it that way.
I see. Okay, thanks.
Okay, great. So in case there's no other questions, I'll continue. So now let's move on to the integrated constraints. So we can deform n equals 4 super-Yang-Mills by a hypermultiplet mass M to get the n equals 2 star theory, as it's called, with sphere free energy f of depending on the mass and tau. So both the mass and tau couple to operators in the stress tensor multiplet, in particular tau couples to the Lagrangian, mass couples to various scalar operators. That means that derivatives of this f of m tau in terms of m and tau will give integrated stress tensor correlators. Because this is just the usual logic that if you have a source coupling to an operator, and if you take derivatives of that source, you get integrated correlation functions of that operator. So the precise relations were worked out in these various papers over the last few years. There are two of them. As you see on the left-hand side, we have various 4 derivatives of the mass deformed free energy at mass equals 0. And then on the right-hand side, we have certain integrals of the 4-point function, which here I've expressed in terms of t and u and v, where the precise form of these integrals isn't so important for this talk. I mean, it's important to do it in practice, but I won't show it because they're a little messy. And then recall that this 4-point function of t, u, and v is then expanded in terms of blocks, including the long multiplet blocks, which has the non-trivial information we care about. So these are the integrated constraints. And the important thing to note about this is that the left-hand side depends on the value of tau. So this is how we're going to input tau. And also notice that we have 2 integrated constraints, and we want to fix 2 things, which is tau and tau bar. Okay, so these are the integrated constraints. So now we want to compute the left-hand side using supersymmetric localization. So localization tells us that you can compute this mass deformed free energy in terms of a rank G dimensional matrix model integral for gauge group G. So for instance, for SUN, this would be an n-1 dimensional integral. Here is the matrix model integral. This is the one you have for finite mass. So just to give a couple details, you have these Barnes G functions. All the theta dependence is coming from this Instanton term, which is called the Nekrasov partition function. And I should note that if you were to ignore the instantons, then you can actually compute this quantity pretty much exactly. So you can do all the integrals, and you can just get the answer for either of the 2 integrated constraints we care about. This I showed originally in my single author paper, and then another paper with Sylvia. Unfortunately, though, we do care about instantons. And that is why we have to do the much harder thing, which is taking into account this Nekrasov partition function. So the Nekrasov partition function, as shown by Nekrasov, can be expanded in the instanton number k in terms of all these instanton sectors. So this is just a matter of notation, but this notation is useful because it shows where the dependence on theta and tau is. So, for each bigger instanton value, it kind of depends smaller because it's an exponentially small term. So these zk's are meromorphic functions. They're related to Young tableau with k boxes. We can use their explicit expressions to compute the various derivatives of mass and tau that we care about. So the calculation was first done in a 1 over n expansion and finite tau in this previous paper. And so we got these very nice expressions that each short on 1 over n, which were modular functions. One of these integrated constraints was actually computed at finite n and tau by Dorgoni, Green, and Wen, which is great because that's what we need for the numerical bootstrap. We want to know finite n and tau. Unfortunately, an expression is not yet known for the other integrated constraint input, which is the 4 derivatives of mass case, because this one's much harder. And so because we don't know both for finite n and tau, instead for this project, I just had to compute them kind of using brute force by just literally taking the matrix model integral, which is n-1 integrals, plugging in the definitions of all the stuff in the integral, and then just doing the integrals. And so the reason why this works is that you can use this instanton expansion, and it converges very quickly within the fundamental domain. Because within the fundamental domain, you always have tau bigger than 1, and these things are exponentially damped in terms of tau. So that means if you include just k up to like 3 or 4, already that gives a very, very accurate expression within the fundamental domain. So that's how we computed these inputs in practice. So here's just to show some plots of what these inputs look like. So let me show the first input, which involves 2 derivatives of mass. So this is for the SU2 theory, and I'm going to describe it in the SL2Z fundamental domain. So here on the left-hand side, we're going from the free theory with Yang-Mills equals 0 all the way up until the Z2 point, where tau equals I. And so as you see, the slope is 0 at the self-dual point, as you expect on general grounds. And then on the right-hand plot, now we're exploring the dependence on theta, because the dependence on theta is very weak on the left-hand side. On the right-hand side, you see it depends on theta, not very big, as you see from the y-axis, but nonetheless, you can see that the largest value is the z3 point at e to the I pi over 3, where again, it has 0 slope there, as you expect. Okay, so this is what the localization input looks like. And because this is the dependence on tau, thus it will not shock you that our results will also look roughly similar to this, because our results are coming from this input. Okay, so the previous slide was showing you what the localization input looked for some slice of the full fundamental domain. On the full fundamental domain, you need a contour plot because it depends on tau and tau bar. So that's what I'm showing you here. So these colors are showing, the values of the localization input as a function of tau and tau bar. The fundamental domain is this middle region. And as you see, it doesn't depend so strongly on imaginary part of tau, which is on the real part of tau, which is what theta is. Because as you can see, the colors are kind of roughly the same. Although it does depend on it. You just have to look very, very closely. Otherwise, it can be a little bit hard to see. Thank you. It is a nice plot. I made it myself. Okay, so now let's talk about how to impose these integrated constraints on the block expansion. So the block expansion of the stress tensor correlator converges in subregions of Euclidean space, but it does not converge over the full Euclidean space. So that means you can't just integrate these I2 and I4 integrated constraints over the whole S4 because you would naively get a divergence. So this is kind of a technical annoyance. And so the way you get around this technical annoyance is that you can divide Euclidean space in terms of various fundamental domains under the crossing symmetry, given by S3. So here in this plot, I'm showing like full Euclidean space, full R2, and I'm showing you the different fundamental domains. So there are 6 fundamental domains because there's fixed, components of S3, but I'm showing you pairs of fundamental domains. And so we're going to look at the region D1, which is the region in which the S channel expansion converges. In fact, D1 is even like bigger than you need. So it converges for some subregion of D1, but D1 is fine. If you were to expand the blocks in the T channel or the U channel, you would just have to look at a different region. So either D2 or D3. But then because all these regions are related by crossing symmetry, if you just do the integral over D1, you could just multiply the answer by 3 and that gives you the right answer. And so that's the way you avoid the fact that this thing doesn't naively converge over the full region. Okay, so in more detail, recall that the block expansion included the short components, which were, you could resum it to these exact functions, as well as the more non-trivial long components. So for the short components, because you just have an exact function and it depends on C very simply, you can just do the integrals of them once and for all just to get some number. So that's very simple. The thing which is way more subtle is the long multiplets, because those you don't know the value of delta and spin. I mean, I guess you know the value of spin, but you don't know the value of delta. And so you just have this expansion in terms of blocks with, in principle, any value of delta, satisfying the unitarity bound. And so if you now want to do the integrals of these blocks, you could use the exact expression for 4D blocks given by Dolan and Osborne. And then for each operator, you'd have to compute a 2-dimensional integral. Something which is much more efficient is to use the radial coordinates introduced by Slava and collaborators, which we call R and eta. And so in terms of R and eta, blocks in any dimension can be expanded at small r, as shown by these authors. We note that at each order in R, you have these B's, which are meromorphic functions in the scaling dimension, and these G's, which depend on eta, are eigenvectors. And so the advantage of doing the expansion in R is that now the R integral becomes trivial because it's a polynomial in R, as long as you've truncated up to some R max. And then there will only be one tricky integral, which is the integral in terms of eta, which you can then just do numerically, but that converges very quickly. So another advantage of doing this R and eta expansion is that if you want to do integrated constraints in dimensions other than 4, for instance, 3, then you would actually be forced to use this R eta expansion. So in 4D, you had the luxury, we didn't have to use it. You could have used the exact blocks, but in general, you would actually have to use this R eta expansion. But it's also just practically useful. Okay, so now let's show what the R2 looks like in terms of R and eta. So the fundamental domain is now given by this region at the bottom in terms of the R and eta space. And notice that this D1 region has its maximum value when eta is 0, at which point R is 2 minus root 3. And so this means if we want to study the asymptotics of the integral of a given block, then we should just look at what the largest value of R is in this domain. And because these blocks in the small r expansion are going like r to the delta, as you see here, or 4r to the delta in particular, times a polynomial in R, that means we know at very large delta the integrals of a given block are going to go like 4 at the maximal value of r to the delta, which is 2 minus root 3. They are also going to oscillate in spin. And the reason is that Gegenbauers, which showed up in this block expansion, at the value eta equals 0, oscillate in spin. So those are the two facts to remember about the integrated constraints, that at large delta, they have a certain exponential growth, and they also oscillate in spin. Okay, so now let's take a step back from the integrated constraints and just review the conventional numerical bootstrap for the stress tensor multiplet correlator. It's shown by Leonardo and collaborators. So you start with the 4-point function expansion. You swap the first.
I mean, I appreciate you call it by Leonardo, but you should at least put our authors in alphabetic order.
Sorry. Yeah.
No worries.
That was not intentional.
No, it's fine. Actually, of course, my co-authors did most of the work, just for the record.
I think there might have been a Freudian slip. I don't know. Sorry about that. Anyways. So by these excellent authors, you swap the first and third operator, you get crossing equations, which when written in terms of this reduced correlator take the following form. So you get the short contributions, which again don't depend on tau, so they're a bit trivial. And the non-trivial stuff is the long multiplets as usual, which depend on the OP coefficients and the scaling dimensions. Then you consider the infinite dimensional vector space, which is given by crossed functions. And then in terms of this vector space, you could think of the crossing equations as an infinite sum of vectors labeled by scaling dimension and spin with positive coefficients given by the OP coefficient squared. And the crossing equations are telling you that this infinite sum must equal a vector of short multiplets, which is what this F0 and F1 are. Then you can consider a functional alpha acting on this vector space, and you can use this functional to bound the scaling dimension and OP coefficients in terms of C, where you know the value of C because you see it's appearing explicitly here. But that's just in general in the bootstrap. You can always put in the value of C because it's proportional to the stress tensor OP coefficient. Okay, so let's just go through all the bloody details because we're going to generalize it in a moment. So the algorithm for scaling dimensions is that first you normalize the functional such that acting on the short pieces, it gives 1. Then you search for a functional such that for generic operators with scaling dimension, delta, and spin, it will be positive as long as they satisfy the unitarity bound, as well as some assumption on, say, for instance, the spin 0 sector, given by this delta 0 star. So if such a functional exists, then by positivity of the OP coefficient squared, we now know that the functional acting on this crossing equation is strictly positive, but that contradicts alpha acting on the crossing equations themselves. And so this means that something we did was wrong. And so in particular, that means for the given value of C that we put in, this assumption on the scaling dimension delta star for the scalar must have been wrong. So that point is disallowed. So then you can do this for many different values of delta star, and this will give you some upper bound on the lowest dimension scalar as a function of C. Now, I should note that for a general conformal field theory, you could also get lower bounds, which when combined with upper bounds give you an island, by putting some gap delta prime above delta 0 star and then interpreting the operator below. But the reason why this wouldn't be useful for Super-Yang Mills, at least in the current setup, is that because it's a conformal manifold and because you're not inputting the value of tau, thus you're putting bounds on the entire conformal manifold, which go all the way from the free theory up to say what the true upper bound is. And so that means the lower bound would always be trivial because they would just be the free theory if you do not put in the value of tau. Okay, similarly, there's an algorithm for OP coefficients, again for spin 0. So in this algorithm, we normalize the functional to act on a specific operator's OP coefficient we want to bound, which we call delta star and spin star. So we normalize that to 1. Again, we require alpha acting on the blocks for all the other operators to be strictly positive. Then we maximize the functional acting on the short stuff, and that will give us an upper bound as follows. So just with the scaling dimension algorithm, in principle, we could have also gotten a lower bound by putting a gap, but that's not useful because we haven't put in the value of tau. Okay, so so far I discussed the abstract algorithms, but as we all know, to actually do this in practice, you have to truncate the various infinities that occur in these algorithms. So the first infinity is very simple. It's just the fact that there's infinite spins that occur in the block expansion. So you can truncate this by simply putting a cutoff, L max. And the reason why this works is that it's shown by Slava and his collaborators, the block expansion converges very quickly at large delta, which is related to large spin. The second infinity is the fact that this vector space is infinite because it's like a full function's worth of a vector space. And so the way we get around that is that we expand this function around a certain point. So in particular, it's convenient to use the crossing symmetric point where z and z bar is a half, and then you take derivatives around that. And if you take derivatives up to some certain capital lambda, that gives us some finite vector space. The third infinity is the range of the scaling dimension that appears in the blocks. So it just says the spin could go to infinity, so too delta can go to infinity, but delta is even worse because now it's a real number. It's not fixed to be integers. So recall that the blocks took the following form, where it was 4r to the delta times some meromorphic function in delta. So this means that after expanding to some R max, taking ZZ bar derivatives, you can then redefine the OP coefficients by some positive factor in order to write the Z and Z bar derivatives of these cross blocks as a polynomial in the scaling dimension delta, where R cross is the value of R when Z and Z bar equals a half. So after doing this, you then, the bootstrap algorithm is then some polynomial in delta. And so it's the statement that some polynomial in delta must satisfy certain constraints. So such polynomial constraints can be solved using semi-definite programming. For instance, STBB, as developed by David, and this gives a very powerful method of solving the bootstrap. So this is the standard bootstrap approach. So now let's see how we have to change things when we add integrated constraints. So now the vector space will have two extra elements, alpha 2 and alpha 4, acting on this bigger vector space, which now includes the integral I2 as well as the integral I4 on your function f. So that means every single step in the algorithm, wherever we had things acting on the v prime part of the vector space, which was the derivatives of v and z bar, now we have to add in these two other elements of the vector space. So for instance, when we're normalizing the functional to 1, the first line is what we had in the standard algorithm, and the second two lines is now what we have, including these integrated constraints. So we have alpha 2, which is basically just telling you that this integrated constraint must be correct. So this is the fact that the integral acting on the short stuff must equal the localization input, and then similarly for the other integrated constraint. And so here you see, this is how we are explicitly putting in the values of tau and tau bar into the bootstrap. Similarly, for the second step of the algorithm, when you're searching for functionals that satisfy this positivity, now instead of just having the Z and C bar derivative guys, you're also going to have integrals on these generic blocks. And so if you can find such an alpha, then this is again a contradiction. This means one of your assumptions was false. And so this disallows points now in the expanded space of C, tau, and tau bar, because we're putting in two integrated constraints. We can parameterize tau and tau bar. Okay, so any questions about how this algorithm was modified? Okay, good. Okay, so now let's see how we could actually implement this in practice, though, because the previous slide was just some abstract algorithm. So let's recall the large delta asymptotics of the integrated constraints versus the crossing equations. So the crossing equations go like 4 times 3 minus 2 root 2 to the delta, as usual, with no oscillation in spin. Whereas the integrated constraints, as we discussed a few slides ago, they have different exponential growth and they oscillate in spin. So this causes two problems. The first problem is that because the integrated constraints oscillate in spin, and because they dominate at large delta because they have bigger exponential growth, this is just going to trivially set alpha 2 and alpha 4 to 0. And so that means you're not going to gain anything by including these integrated constraints. You're just going to get the standard bootstrap as if you didn't know the value of tau. So that's a problem.
Sorry, can we disentangle the two issues, the oscillation in L and the domination? What if they did not oscillate in L, you still have the issue that they dominate a large delta, so you still set alpha 2 equal to. So I'm a little bit confused by what you put them in the same sentence other times.
Oh, well, okay. So I mean, I guess if they had the exact same exponential growth and if they oscillated in spin, I guess this would be a problem. I guess it would probably also be a problem. I mean, it would only not be a problem if I guess it had sub-exponential growth. And because then it probably wouldn't matter. But the exponential growth will always be, I guess, as big or bigger.
But what if, suppose that the exponential was the same, but they oscillate in spin? Would that be a problem?
Well, I think it would still be a problem because you'd be making a statement that like a sum of a bunch of things has to be positive, but two of those things are oscillating in spin. Okay. And if all the things are contributing roughly the same way, then it would still demand that those two things. Well, I guess it depends. I mean, it's kind of subtle because I guess it really depends on the exact coefficients of all the terms in your sum. I mean, if you're summing a bunch of things and like they have to overall be positive, and if maybe the first 10 are really, really positive, then it wouldn't matter so much if the last 2 are slightly negative.
Okay.
Yeah, so it's kind of subtle. I mean, I guess it would depend on the details of the problem. But in any event, the oscillation in spin is not an issue, as I'll explain in a moment. Maybe I shouldn't even mention it. The second problem, which is more serious, is that the integrated constraints scale exponentially bigger than the crossing equations. So this is the more important problem. And this is a problem simply because you cannot approximate both by a polynomial because they have different exponential scaling. So you can't take off the same exponential for both. So one naive thing you could try to do is you could try expanding the cross equations around some point other than the cross-symmetric point, such that you get the same exponential scaling. But if you do that, then the cross equations would start oscillating in spin, and then you would have the usual problem of oscillations in spin. So life would even be even worse. So you don't want to try expanding around something other than the crossing, the cross-symmetric point, because that's going to make things worse for you. Okay, so there's these two problems. Let's talk about how people address these problems in the past. So there was a previous paper in 2 dimensions by these collaborators where they also had integrated constraints. They also combined it with the numerical bootstrap for some other supersymmetric theory. The integrated constraints had a different origin, but they took roughly the same form at the end of the day. And so the way they got rid of problem number 1, the oscillation in spin, is that instead of doing the integrals just over this region D1, you could make the region, you could push the region into D2 and D3, so you make it a little bit bigger. Now, the maximum value of R would occur when eta is not 0, so that Gegenbauers don't oscillate. So as a result, your integrated constraints do not oscillate in spin. And then you could take into account the fact that you made your region a little bit bigger by just subtracting off that extra piece after mapping it back into the original fundamental domain. So this is why I'm saying oscillations in spin are not a problem. Like there's a known way of getting around them. It was shown in this paper.
Hi, Shai, I'm sorry. I don't remember how they did this, but at this point, the way you presented, I'm confused, because if you show that E2 of G delta L oscillates in spin,
yeah,
how, I mean, whatever you do, you can slice and dice the regions whenever you want, but in the end, you still compute E2 of G delta L, and it will have to oscillate in spin. So
no,
how can you solve this problem by slicing and dicing? I don't understand.
Okay. So the subtlety is that the only thing which is invariant is the full block expansion. So like your ability to choose different integration regions, that is invariant when you consider the full block expansion. But specific
when you consider the full
are not invariant. Sorry.
Okay, I see.
So specific blocks will change. So the only statement is that the full thing will remain the same. And
so you're saying, using the fact that the 4-point function is crossing symmetric, you kind of subtract and add certain things to individual block contributions.
Yes.
And achieve that sum of, and that things don't decide. Okay, thanks.
Yeah, exactly. Yeah. So like that is a subtle point. Thanks for the question. Anyways, yeah. So they solved it in this previous paper by just choosing this weird region. And so this is why you don't have to worry about oscillations in spin. So it's not a problem. I should note though that by choosing this weird region, it just makes the value of Rmax even bigger. And in particular, there is no region you can ever choose which would make the value of Rmax smaller than the value I showed you before, which is 2 minus root 3, because like that's the absolute minimum. So that means no matter what you do, no matter what region you choose, you're always going to have different exponential scaling between the integrated constraints and the crossing equations. So that's why this is the real problem. So the oscillation in spin is not a real problem. We know how to solve it. The bigger problem is the exponential scaling and the fact that that's different. So how did they get over that problem? Well, in the 2D case, they did something, I guess, very simple-minded, but nonetheless it seemed to work, which is that they simply just approximated an exponential by a polynomial. And so that sounds kind of crazy, but apparently it worked in their case. It worked in the sense that they were able to have sensitivity to their integrated constraints. On the other hand, it just didn't work in our case. So like when I tried doing that for 3 years, I kept getting trivial results. So I was getting no dependence on the integrated constraints. And I can also comment that like I've tried analogous problems in 3D, and it also didn't work when you try to just approximate this exponential by a polynomial. So instead, the way we got around this is that we went back to the original bootstrap approach in Slavo's original paper with these collaborators. So before people started doing semi-definite programming, the original way of bootstrapping was just to discretize delta up to some delta max for each spin. And then you just have some finite number of constraints, which you can solve with linear programming. So it's kind of more simple-minded than trying to do this fancy semi-definite programming. And this works because for sufficiently small discretization and large enough delta max, the numerical results are unaffected. So the same way that like as long as your Lmax is big enough, you get monotonically improving bounds. So too, if your discretization is small enough and if your delta max is big enough, you also get monotonically improving bounds in terms of Nmax. And so from this linear programming approach, there's just no issue with like the exponential scaling because you've put in a delta max. And so you're not in principle looking at delta all the way up to infinity, you're always looking at delta up to some cutoff. And so that means in terms of that cutoff, as long as you use enough precision, your optimization program will be aware of all your constraints and they will all be taken into account. And so this is how we avoided the problem. In fact, as long as there's a delta max, it doesn't even matter if the blocks oscillate. So like we could have chosen some regions such that the integrated constraints didn't oscillate, but it didn't matter. I mean, we tried both. We tried both oscillating regions as well as non-oscillating regions. We got the exact same answer. And so, yeah.
But isn't this now a bit delicate? Because you're saying if you send delta max to infinity too early, the integrated constraints don't matter. So where do you stop?
Well, so it's basically a game you're playing where it's like the bigger value of delta max, the more precision you're going to have to use.
Well, no, actually, when we wrote our paper, since I still remember this, we were careful about this point. So we checked that our functionals actually were remaining positive for, even though we were cutting off delta max, we checked that in asymptotically high delta, our functionals were still positive. And for this, it was important that things did not oscillate. So I would be careful. You know,
okay.
I would be more comfortable if you use the trick to get rid of oscillations before you apply this method.
Okay, so I agree conceptually it would be cleaner to use the non-oscillating region. And I also agree that our functionals will probably not be positive for arbitrarily large delta. But I guess for practical applications, that doesn't actually affect the results. But I agree that like it's cleaner and conceptually nicer just to use the non-oscillating region, because then in principle, your integrated constraints should be positive, I guess, for any value of delta.
Yeah, but this is, I mean, sorry to harp on this, but this is a kind of a crucial point, because you're going to show us in a minute a plot where you get stronger bounds everywhere on the conformal manifold by imposing these integrated constraints.
Yeah.
And that, I think, is in some sense the main message of your work, that somehow, surprisingly to me, at least I'm a little surprised, the bounds without inputting the integrating constraints are not saturated anywhere on the conformal manifold if you impose the integrated constraints. But then
you're jumping ahead a little bit though.
Yeah, we'll see.
Well, okay, I can just show you right now because it's the next slide. Okay, so
sorry,
okay, so
Shai, maybe it's just me, and if it's just me, you should say it. But the scaling, the large delta behavior of the conformal blocks, this road to the delta, it doesn't really enter in SDPB, does it? It enters somehow in some choice of bilinear basis. But otherwise, we just shove that factor into the OPE coefficients.
I mean,
that's what I thought.
I mean, okay, so I guess there's two ways you can discuss this. So first of all, if you're trying to use semi-definite programming, then obviously it enters simply because you're trying to approximate something as a polynomial. So that's why.
No, but it doesn't, right? We don't approximate that exponential factor as a polynomial. We approximate what remains as a polynomial. We just lump the exponential factor into the OP coefficient.
Yeah, but the way you got rid of that factor is you have to redefine the OP coefficient everywhere by that factor. But the thing is that if you have two quantities which have different exponential scaling, you can't remove two different exponential things at once by just rescaling one quantity. So it's like, say I've already removed 3 minus 2 root 2 to the delta, by redefining my OP coefficients. Now I can't do that again. I can only do that once. But normally
okay. So you say it's the same. I see. Very good. So it's the same block that enters. Thanks. Yeah. Okay, I got it now.
Okay, great. Anyways, yeah. So I guess anticipating what Leonardo was about to talk about. So these are the actual results. So for anybody who wasn't following, this is all you need to understand from this paper is this slide, because these are the results. So please pay attention to the slide if you didn't pay attention to anything else. So on the left-hand side, we show the results of our algorithm on a certain slice of the fundamental domain. So this is going from weak coupling on the left all the way up until the Z2 point. The orange is the allowed region, white is disallowed. The black line is our results with integrated constraints. The gray dotted line is Leonardo's results, although I should say we redid his results just so that they would be done in the exact same context. So the gray dotted line is the results you would get without integrated constraints, but otherwise using the exact same parameters. So same values of spin, same nmax, etc. And so as Leonardo was saying, you notice that this gray dotted line does not touch the black line throughout the fundamental domain. So that means the upper bound you were getting without the integrated constraints is never saturated by the physical theory. So the really nice thing about this plot, though, I should note this is for the SU2 theory, although we also have similar plots for SU3, and you could even do higher if you really wanted. So the really nice thing about this is that if you compare it to the weak coupling estimate for this lowest dimension scalar, which is called the Konishi in weak coupling, you see that it very beautifully saturates this bound in the weak coupling regime. And in fact, it saturates it for an even larger value of G-Yang mills than you might have naively had expected. Because after all, weak coupling estimates, these are asymptotic series. Maybe it should have only worked in the very small region, but here it's working all the way up until like 0.5, which I think is very nice. And you can see also that each loop makes it even better. Yeah.
Shai, a quick question. So for this plot, if you look at this tau and n equals 2, what is the size of the instanton correction to the, because it's to the Canisian anomalous dimension? It has been computed, right?
Yeah, there's been papers about that, but like I don't know. Well, okay, I don't know how much I trust those papers. I mean, like,
But what if we evaluate it and add it to this plot? How big is it?
Well, okay. So first of all, in the weak coupling expansion, it's not clear to me that people have been able to successfully compute instanton corrections. Although maybe I'm wrong. I know there were some papers, but it's not so clear to me they were able to do that. I mean, one thing I can tell you is that for our localization inputs, the instanton corrections are pretty small. And so like that, what I wanted to emphasize is that on this left-hand plot, the dependence on theta you can't see by eye. So these upper bounds, these are kind of upper bounds on like the maximum of every possible value of theta, because you just don't see the dependence on theta by eye in this regime of G-Yang mills. And so like, I would strongly suspect, I mean, these are our bounds. I would strongly suspect that the true answer, which I'm conjecturing is saturating the bound, 2, does not really depend on theta within this regime of G-Yang mills. So, and in general, the dependence on theta is very weak, because you saw from the plot of the localization input, so that rainbow plot from 10 slides ago, you saw that the dependence on theta was always weak, but it is strongest when G-Yang mills is biggest, as you might expect, within the fundamental domain. And that's what this right-hand plot is showing. So the right-hand plot is going from the Z2 point to the Z3 point. And here you see that the upper bound is changing with theta, albeit in a very small way, and that the maximum value appears to be the Z3 point. And I can tell you that the SU3 plots are qualitatively similar.
Okay. Hey, a couple of questions. So first, in the original work by Beam et al., if I remember correctly, the spin 2 and spin 4 numerics were more convergent than the spin 0. Isn't this a good reason for you to go to the higher spins so that you can make the claim that there's a gap stronger?
Okay. So that's actually an interesting question. So like, I was very surprised to observe that for some reason our numerics were less converged for larger spin, and I don't really understand why that's the case. And maybe we just didn't look carefully enough. But like, I mean, so we've mostly just looked at spin 0. We looked at spin 2 a little bit, and it seemed like the numerics were converging slower. And yeah, and that's weird because like without integrated constraints, converges faster. So I don't have an explanation at this point. I think it's an interesting thing to look into more.
Yeah, I agree. And I think it would help bolster the claim that there's a gap between the optimum without and with integrated constraints, because you might have said that the best bound they got without the integrated constraints was not optimum yet because the numerics didn't seem to converge. So maybe that line would come down and there's not really a gap. Okay,
sure.
That's the point.
Although I will say though that like these two bounds were computed with the exact same values of Nmax. And so and also, I mean, these results are like reasonably well converged. Like the value of Nmax we used, I don't know if I say it on the slide somewhere here, but like it's pretty big. It was like, I think it was, yeah, I say it right here. So it's capital lambda equals 39. So that's Nmax equals 20. So that's a pretty big value. I mean, I think that's like as big or maybe slightly bigger than the values they used in their papers. I mean, they can correct me if I'm wrong. And so at that value, things are like reasonably well converged. I mean, they could obviously converge more, but like, you know, it's like, I don't think this plot's going to change so much as lambda increases. I mean, it's certainly the plot on the left-hand side.
So are you saying that adding integrated constraints for this plot improves the bound, but also improves convergence?
No. That's what I'm saying. No, I don't think it converges. I don't think it improves convergence. I think convergence is the same, whether or not you integrate constraints or not. And I think it's pretty well converged when lambda equals 39.
But in their plots, convergence was not very good, or maybe I remember it wrongly because you have to extrapolate.
Bad convergence just means you have to look at very large lambda. We did look at very large lambda.
Ah, okay.
Yeah, so like lambda equals 39 is a very large value.
But you're confident that this procedure you're doing with this delta max that you kind of put some value which is not too high enough but not too high is completely kosher.
Yeah. Because we played around with different values of delta max. You know, we played around with different values of precision, and we made sure things didn't change.
I mean, if this is the truth, we should of course embrace it. But it does raise our speculation that the bounds without integrating constraints are saturated by physics was, of course, just a speculation. We had no very strong reason for it.
Yeah.
But then the moment that that is falsified, then that opens the Pandora box of skepticism everywhere. Why should I then believe that your plot with integrating constraints is saturated by physics? I mean,
Well, the reason why I should think that is because the comparison to weak coupling.
Okay, maybe, but
Leonardo, it's easy to check there. So even if they didn't check it, but they could take their functionals produced with finite delta max and just plot them in the region for high delta max and see if they remain positive there or negative. If the functions for larger delta max are negative, then I would be skeptical. But if the functionals remain positive also for larger delta
that's
max,
a good point. That's a great point. Yeah.
Then they would be self-consistent.
Look,
I don't know. If,
I agree that moving forward, we should just use the region with no oscillations. And we already have that implemented, so we can easily do that. And we should do that.
Shai, can you also say, so the paper about the instant corrections that I'm familiar with is by Eldai and Korchemsky, where they claim to compute the leading instanton correction to the Konishi anomalous dimension. It doesn't come at leading order in perturbation theory, but it comes to subleading order, and they compute it, they get a number. Can you say why you're skeptical of it?
Okay, so I just remember that at some point I looked into this paper a couple of years ago after we came out with the paper with Michael Green, because somebody, I guess the reviewer asked, like, how does these two things relate? And I remember there was some things in the paper just didn't make sense to me. Although, like, I don't remember the precise objection. So I just remember, like, something seemed a little bit fishy at the time. Because like we have computed instanton correct. Okay, so there's a different limit, which is the very strong coupling limit, which is where n is big and tau is finite. And in that case, we do know the instanton corrections to, the lowest dimension scalar, because, we know the answer just in Eisenstein series. So we know all instanton corrections. And so I think at the time they were trying to ask if, like, you could somehow relate those to the instantons of the weak coupling limit. I mean, I guess maybe the answer is just that you just can't relate the two because they're two completely different limits and instantons look completely different.
That's what I would say.
Yeah. Okay, look, I don't want to make any big claims. For all I know, the paper is totally kosher. I just remember being confused about some things at the time, but maybe it was just my problem.
Thanks.
Yeah. I mean, okay, just one thing people have tried though is that I remember after Beam et al.'s paper came out, there was various attempts to try to improve these weak coupling estimates to make them modular and invariant, and those I think were a bit more speculative.
Sure,
yeah. But perhaps the claim is that at least.
Well, I mean, it's not that they were speculative. There was a large error, so I don't think. It will contradict anything, but
okay. So, but just to make one more comment about this discussion about whether or not the original bounds were saturating something. Like, I don't know why you would have expected anything to saturate it, because, like, you're just looking at one 4-point function, right? So it's
but then I cannot make the same criticism here. Why would this? You're just adding two constraints out on top of infinitely many, right? I mean,
sure,
not you're adding much.
But I'm not claiming. Look. I doubt that, like, the upper bound is literally saturating the literal theory. I'm just saying it's getting closer and closer and closer.
Okay, maybe that's what we should say, that it's getting closer.
Look, I think the more accurate claim to make is that the more constraints you put in, the closer you're getting to the physical theory, and we're pretty damn close based on the comparison to weak coupling. But, like, because I think it's pretty impressive. But, like, but I'm sure it's not exactly on the upper bound. And, like, the way you can get more evidence for that is you can just keep adding more constraints and see how things change. And so, but that's what I wanted to discuss. Okay, so here's the plot for the full fundamental domain of the upper bound. So this plot looks somewhat similar to the localization input, so it shouldn't surprise you. Okay, so to give a bit more evidence that this upper bound is really corresponding to close to the physical theory, maybe not exactly the physical theory. So remember that in the Ising model, the way people got islands is that they had to put a gap and then insert operators below that gap, because you can get an upper and lower bound. So these previous plots was with no assumption. So that's why we're just an upper bound. So ideally, we would want to say there's just two relevant operators and then put a gap to 4, insert those two operators below, and then we would get upper and lower bounds. And so we would get, like, islands for each value of tau. So we think that will work eventually. But in order for that to work, we have to know the second lowest operator very accurately. And as all bootstrappers know, the higher the twist the operator, the harder it is to know accurately. And so at our current system, we don't know the second lowest operator accurately enough. And that's why when we put a gap to 4 and insert two operators, we would just get upper bounds. So what we did in the interim is that here we're just inserting other gaps. So we're not we're not like putting in two operators, putting a gap to 4, which would be more rigorously justified. Instead, we're just putting some gap above the lowest operator. And as usual, when you put a gap above an operator, you always get some kind of lower bound. And what's interesting is that this lower bound seems to be converging to the upper bound. So the upper bound is not changing as we put in this gap, but the lower bound is. And it seems like it's
Sorry,
converging.
which gap again? Sorry, can you repeat which gap are you?
Okay, so we're looking at the spin 0 sector. We're inserting an operator called delta 0, and then we're putting a gap above delta 0, and we're allowing all operators of that gap and higher. So for instance, on this left-hand plot, like say, you know, in this region, we're inserting this operator, I guess going between like 2 and like 2.8 roughly. And then we're putting a gap for the light yellow region is 3, and the dark yellow region is the gap where we've put it to 3.5. But the important thing to notice is that it's the same upper bound for both of these regions. The only thing which is changing is the lower bound.
Okay.
But
And
why would this operator, why would this gap be expected to be independent of G-Young-Mills
No,
in the physical theory?
Well, okay. So this gap would certainly depend on G-Young-Mills. And so that's why this thing is just kind of like a half step. Like the more clean, rigorous thing, which we intend on doing, is putting a gap to 4 and inserting 2 operators below. Because then, of course, the gap at 4 will not depend on G-Young-Mills, and then we'll just scan over those 2 operators, and then we hope to get islands in the space of those 2 operators. But as I said, in order for that to work, the bootstrap needs to know that the second lowest operator is below 4. And like right now, the bootstrap's knowledge of the second lowest operator is vague enough that it's like a little bit above 4, a little bit below 4.
But why do you have to do? Why can't you just extract the second operator by extremely functional method, and that's going to be the maximum allowed value of the gap? But it's going to depend on G-Young-Mills. I don't understand.
Yeah, you know, you could, but like if you were to look at the boundary and extract the second lowest operator, you would find that it's above 4 right now, and we know that's obviously wrong. Because at weak coupling, we know that the second lowest operator is below 4.
Well, how can this be true then? Then it's not a physical bound.
No, you know, it is a physical bound. It's just that no one's claiming that at this level of precision, the upper bound is exactly the physical theory. But I mean, this is the case with anything. I mean, like if you were to look at the icing model, you know, the current icing model done at very large Nmax in David's latest paper, and if you were to look at the boundary, and if you were to extract the spectrum, the operators you're extracting would not be at their precisely correct values. You know, like you know, somehow God told you the answer of precisely like the 5th lowest twist operator, and if you compare it to the spectrum, it wouldn't match the spectrum exactly. That's simply because, you know, the spectrum fluctuates as you improve Nmax.
Well, it fluctuates, but not to such an extent. I mean, here you're saying you're basically like making an order of order 1, while in David's spectrum, the error is.
But it does. I mean, the higher the twist the operator, the more it fluctuates. So, like, you know, even in David's light cone bootstrap paper, he was only able to get accurate estimates for the lowest 2 twist operators, and that's for the icing model, which is like the absolute simplest theory. And so, like already, like the 3rd lowest twist, he wasn't able to get accurate estimates. And so here we're talking about the second lowest twist operator. It's an operator whose dimension is around 4. And so we're going to need, you know, a lot more bootstrap accuracy to get it accurate. So I don't think this is so surprising.
I think another way of saying this is that this is sort of evidence that the upper bounds from the previous plot are not actually saturated by the true n equal 4 Superang-Mills theory.
Oh, sure, I agree, but
that one would be in the allowed region.
The icing model. I'm just saying it's the exact same story with the icing model. Like in the icing model, like the true physical icing model is not actually saturating literally the boundary of these incredibly tiny islands. And you know that because if you were to look at the spectrum is not precisely the same as like the true icing model known by God. But like that doesn't worry us as mere humans because like we just want to get like a reasonably accurate expansion for like the lowest operators. And so in the icing model, they have it accurate enough that you can get maybe the lowest 2 operators to pretty good accuracy. So far in this bootstrap, we've gotten the lowest operator to pretty good accuracy. And our goal is to get the second lowest operator. But there's absolutely no conceptual difference though between the icing model and what I'm showing you right now. Any further, I guess, comments on that? Okay, so let's just move on. So we can also compute upper bounds and OP coefficients. So these also match weak coupling. The matching is a little bit weaker simply because for these OP coefficient plots, there's kind of an extra source of uncertainty where first we had to like assume that the theory is like roughly saturating the upper bound, put in that value of the scaling dimension, and then compute the OP coefficient. And so it's expected they won't be as accurate, but qualitatively they show the same features. Except one qualitative difference is that it seems like the maximum of this upper bound is actually not at the Z3 point, is actually at the free theory, which I guess is slightly interesting. Anyways, okay,
Shai,
so
Shai,
yeah.
Sorry. Can you explain the minimum on the upper left plot, please?
Here. That's actually a good point. Yeah. I don't have an explanation for that minimum. Yeah. So I guess it's interesting. So like, well, why is it the OP coefficient upper bound goes down and then up? Yeah. So yeah, that'd be interesting to understand.
Thanks.
What's the value of delta zero here?
So I mean, you would have to look at the other plot and see what it is at around this value. So
Something.
say this is around 0.3. So you would look
Yeah,
at this
but you
plot.
take it to be the one. Okay,
So I guess it's around like
take it the one that
2.5.
saturates the bound.
Yeah. So yeah, we were just assuming that, we're assuming the physical theory roughly saturates the bound, and then we're creating the OP coefficient corresponding to that.
Okay.
So this plot has a bit more uncertainty. Yeah, but it is interesting that it goes down and then up, because then you can ask like, what's special about that minimum? Anyways, okay. So in conclusion, we showed how to combine integrated constraints with a numerical conformal bootstrap in general. And so I was talking about n equals 4 Sebring Mills, but I think this same approach should work in any dimension as long as we have integrated constraints. In particular, we apply 2 localization constraints for n equals 4 Sebring Mills to bound CFD data in the stress tensor 4-point for any gauge group and tau. In principle. In practice, so far we've done it for the lowest dimension operator called the Konishi, as well as its OP coefficient for specifically the SU2 and SU3 theory, but for any value of tau. So without putting any gap or any assumptions, we got an upper bound which was separated by weak coupling to 4 loops, which I think is very non-trivial. If we put in some gap, which depends on tau, which is a bit arbitrary, then we see that we start getting some small islands for each value of tau near the upper bounds. And also we noticed that the maximum of some of the CFD data, the scaling dimension, was at the Z3 self-dual point, although apparently not for the OP coefficient. So there's many future directions, some of which we're working on, some of which I encourage other people to work on. So one thing is that it would be nice if we could get both of these localization inputs for a finite value of n, because then we could just do what we're doing for any value of n very easily. And so as I mentioned, one of those inputs has already been computed for a finite value of n, but the other one hasn't. And so that's an open problem. Of course, if you want to look at the regime of lambda where theta doesn't matter. So for instance, like say you wanted to compare to integrability or something, then you could already do that because we already know the values of these localization inputs if you ignore the instantons for any value. The other more important thing we'd like to do is improve the bootstrap accuracy such that we can see more of the spectrum. So in particular, as we had this lengthy discussion, we really want to see this second lowest operator, so the other relevant operator. Because if we can see the second lowest operator accurately, then we can impose a gap at 4 and get rigorous islands. And I'm confident we can do this. I think it's a matter of time. So one naive thing would just be improving the value of nmax. Because after all, convergence maybe is not as fast as it should be. Maybe if we did nmax 100, we would already get enough accuracy. Something a little bit more intelligent, though, is that we can take advantage of the fact that there are not just 2 integrated constraints, but there are in principle infinite integrated constraints. And so what do I mean by that? So if you look at the 4-point function with 2 stress tensors, SS, and then 2 other half PPS operators. So you have a different half PPS operator for every P. So like P equals 2 is the stress tensor, P equals 3, 4, 5, 6. So for every value of P, for 2, 2 PP, there's a different integrated constraint. And so by looking at mixed correlators involving more of these higher half PPS operators, we can include more and more independent integrated constraints. And so that's why things will get better and better and better. And that's actually an advantage of this setup over the IC model. So in the case of the IC model, the only things you could put in was the fact that there was like a few operators that are relevant. And that's kind of it conceptually. And then after that, it's just a matter of kind of like improving your numerical, tricks. Whereas in this problem, there's actually like conceptual things that you can keep putting in, which are these new integrated constraints. So in particular, the next thing to do is to look at mixed correlators involving the P equals 3 operator. So this mixed correlator bootstrap study was previously done by these authors and clarified by me in a recent paper. The localization input has been computed, including instantons. So we know how to compute the Nekrasov instanton function when deformed by this P equals 3 operator. And so everything's kind of ready to go. It's just a matter of implementing it. And so the hope is that by looking at this mixed correlator system, we will be able to get the second lowest operator precisely enough such that it will be below 4, and then we can get islands. So that's kind of like the main big goal at this moment, is to do that. But once we can do that, then of course we would like to do it for general values of n, and then we could see all kinds of interesting physics. So for instance, we could see the fact that as you go from small n and weak coupling to large n and strong coupling, the spectrum of operators should become smaller. This is something which we already understand from integrability, but we could also see it now beyond leading order and large n, which I think would be nice. The other thing I want to emphasize is that the method we're introducing here is extremely general. So like we've demonstrated for n equals 4 super-ring mills, but this idea of combining localization and bootstrap can be done for any theory in which you can do localization. And so that means any 3D n equals 2 theory, any 4D n equals 2 theory, and any 5D n equals 1 theory, because you can do localization in all those cases. And so the same way that we are very close to solving the n equals 4 conformal manifold, we could do it, for instance, for the 4D n equals 2 SQCD theory, which also has a one-dimensional conformal manifold. That's something I'm looking into at the moment, because in that case, localization is understood. You can also just compute the instantons concretely. One could also look at 3D n equals 6 ABJM, specifically the n equals 6 case, because n equals 8, we already think we were able to kind of fix it by putting in the one localization input. But to fix n equals 6, we need a couple more inputs, but we have them as integrated constraints. And so we think we should be able to kind of like fully parameterize that theory and see how it goes from string theory to M theory to the higher spin regime, which I think would be very cool. You could apply this to like, literally any 3D n equals 2 theory. So for people who are interested in the super icing model, you could start implementing these integrated constraints. You could study, like super QED. You could study 5D theories if you really care about it. I think there's just like a very wide class of theories that can now be studied using this method. So I encourage any interested students to contact me and, start working on all these projects.
Okay, thank you. Any other questions?
I have a rather comment. At some point you mentioned that you have a decoupling upper bound for your region going big perturbative expansion for Kanishi. And actually there is simple reason for that, which I try to explain in a moment. Yeah, this one.
Okay.
Imagine I will neglect Instanton corrections because we agree they're small values of G. If I'm staying only with the perturbative approach, and I'm talking about correlation function itself, then you could show, because basically of n equal 4 supersymmetry, this correlation function could be constructed perturbatively loop by loop over some basis conformal integrals. And then we ask the question, how many free parameters will appear in this expansion? And the answer that we know right now is that up to 4 loop, there's only one parameter which is free, which means that if we just fixed one loop correction to this correlation function, there's some regular procedure how we construct the integrand up to 4 loops. So now I'm taking one of your integral constraints, and I will just put my ansatz for correlation function into the integral constraints. Then I would say that this constraint will fix me the only constant which I need to get for loop prediction for the Kanishi.
Yeah.
And I believe that what you're just showing on this picture is more or less the same.
Well, sure, but we're doing this in principle at finite n and finite g. So like, I agree that like you could do the weak coupling approach as you said, and I guess you'd be able to fix, this free parameter. But like, we're just comparing to weak coupling. Like we didn't do this at weak coupling. We did this, at finite g.
No, I understood that, but at first value, if I'm asking the question why the upper region of your allowed region goes perturbative expansion.
Okay, but is that so obvious though? Couldn't the allowed region have been like way higher? Like, or are you saying that like somehow like I guess within that region like the block expansion organizes itself automatically as you're saying, such that there really is only one free parameter, thus it's like more likely that it would be saturated?
No, I'm simply saying that if I look for very small values of G, so even though your calculation was done on finite G, finite n, so I'm just looking for region of small G. And I'm asking, for example, just for the slope of this curve, obviously this slope will be very close to perturbative expansion.
Yeah.
Then if I go further, if I go to larger values of G, so I just going away from small values of G and then asking the question whether perturbative expansion make any sense in this region. And it does if you know from the very beginning that instant will give you negligible contribution.
Yeah.
And it does for small G. So therefore, there should be some region in G in which I am allowed to forget about instant correction. And in this region, small G, I will be allowed to, at least in first approximation, to believe my perturbative expansions. And I'm saying that perturbative expansion in this region for small G depends only on one parameter. And if you fix this one parameter by whatever methods, then you're done with at least recapping expansion of condition to a sufficient number of loops.
Okay, sorry, but I want to understand a little bit better. When you say it's fixed by one, I mean, fixed how though? I mean, like it's like
Thinking you start, you have 4-point correlation function.
yeah.
So you're just writing some ansatz of this 4-point correlation function, and you're imposing the condition of conformality, as well as the conditions that your correlation function moves operator, which in sense will multiply as Lagrangian. These two
Wait, so-
conditions alone.
But how did you know what ansatz to put in? I mean, like, I'm sure the ansatz you guys use is the right ansatz, but like, you know, from a very abstract, you know, bootstrapper's perspective, like, how would you have known that like
No,
the
no,
component blocks, you know, had to be written in that ansatz?
No, from Bootstrap, I don't know answer to the question. But simply what I'm saying is that in your Bootstrap approach, you imposed the conditions for these two integral conditions for the correlation function. These are part of your Bootstrap program.
Sure. Okay. So if I understand correctly what you're saying, you're saying that within the small G-Mills regime, there is like a reason to believe that the full 4-point function is fixed in terms of just one parameter. And so that as long
up
as
to 4 loops, let's be more careful. Up to 4 loops, we know this for sure. I don't know.
Yeah. Okay, but why is that so different from the general logic of just saying that for any value of G-Mills, we think the full theory is fixed in terms of 2 parameters, and so we put in 2 parameters, and so thus, you know, we should have fixed the theory. I mean, like, I think the logic is pretty similar. Like, but in both cases, I don't think it's guaranteed that the upper bound would have been saturated by like the physical theory, because like, you know, I mean, it could have been that like upper bound was way above the physical theory, and that like, you know, even though in principle you fixed it because you only have one constraint, you know, that's not enough to actually fix, you know, all the non-perturbative data within this 4-point function.
No, but my logic, I don't know.
Misha, why is upper bound is saturated, not say lower bound?
No, but
For example, if you have the logic, if your logic explains any of the bounds, then you have to say, why does it explain upper bounds and not lower bounds? Because he doesn't have any lower bounds. So there must be something special about your logic that it only applies to upper bounds. What is it?
Well, in principle, we have lower bounds.
Once again, maybe. So in your Bootstrap program, you added 2 additional conditions, which are conditions for integrated correlation function. These are part of your Bootstrap program.
Sure.
We agree on that. Then I'm saying, let me choose among all conditions which are imposed, just only one equation, which is integrated correlator equal to something which you know from localization.
Okay.
My logic is like this. For me, it's sufficient just take only this one equation, which part of your Bootstrap program, just to fix correlation function, let's say up to 4 loop, unambiguously.
So you're saying that he should have actually found also lower bound, and that the lower bound and the upper bound should be very close for small G. I mean,
Yes.
that is basically what you're saying.
Yes, if you wish.
But okay. Okay. Any other comments or questions?
Maybe Shai, on the previous slide, or the one you showed before, I think it was the one for this one for delta 0. So indeed, I think in our second paper we did an extrapolation to infinite lambda for the result, of course, obviously without integrated constraint, and so you have a value of about 2.96, 2.97 here.
Yeah.
And our extrapolation looks like a pretty sort of qualitatively very similar behavior from lambda equals 25 to 39. And then the extrapolation would give you something like 2.93 for infinite lambda. So it comes down a little bit, but not enough because you're obviously at 2.86.
I think we actually made that comparison at some point. Yeah, and I think it was still no noticeably different.
Right. So this is just to stress Leonardo's point that the extrapolation of the single correlator result seems to meaningfully differ from.
I mean, I wanted to give one more comment, which is that at large n, I do think it is likely that the upper bound without integrated constraints is very close to the physical theory. I mean, in some sense, for super large n, we know that has to be true because in the plot from your paper, which I showed in the very first slide, you saw that it was true, where you compared supergravity, which is the leading 1/n correction, which doesn't depend on lambda, and that was very close, to the extrapolated version of the upper bounds. And that's something we can kind of see happening. So it's like, I didn't show you the SU3 plot, but if you were to look at the SU3 plot, the difference between this gray dotted line and the upper bound is smaller than it is for the SU2 plot. And so this is a trend which I expect will happen, is that we look at larger and larger n, the discrepancy between adding integrated constraints and not adding integrated constraints for the maximal value will become smaller and smaller, such that at super large n they'll be indistinguishable. And so like, I don't know why that's the case. I mean, it's probably related to the fact that as n becomes very big, the dependence on tau becomes weaker, because we know that in the supergravity regime, it just doesn't depend on tau at all. And so I guess maybe that's kind of expected.
Mhm. Right,
And
but it
also,
still
like,
leaves the puzzle of this plot, right?
Yeah. And then one more comment I can make is that you could have asked a similar question in the context of the ABGM bootstrap. So like when we originally did this ABGM bootstrap, we did it without putting in this localization value of the OP coefficient. We got a certain upper bound, and it seemed very close to independent computations of this specific CFT data. And so we were like, okay, maybe it's saturating the bound. But then in a later paper, when we actually input the value of the OP coefficient and reran that bound, it didn't noticeably change. And so like, in that case too, it's clear that like the more stuff you put in, you know, the better the bound came, and like the closer it came to like what the actual physical theory is.
Do you know what happens in the 2D case where the numerics were more straightforward? They integrated imposing or not imposing. Does it change things quite significantly?
I actually, that's a good question. Yeah, I don't remember. I mean, are any of those authors in the audience? So David and Shai and Yin, perhaps not.
Okay, anything else? Okay, if not, we can thank Shai again and see you next week.
Thank you.
Thank you.
Thank you.
Right.